Structural systems are assembled by putting members together at joints. We're familiar with the different structural members. Now we focus on joints. Unfortunately, the joints are often the weak points in a structure and can be the source of failures, like here in the San Francisco-Oakland Bay Bridge after the 1989 earthquake. So, let's take a closer look at joints.
The simplest kind of joint or support may be the roller. This bridge in Cologne, Germany is on real roller supports. You might ask why rollers are useful. Let's take a quick look at the behavior of the Cologne Bridge.
Let's do a quick analysis on the Cologne Bridge. We've got three spans, 140 feet, 280 feet, and another one at 140 feet, for a total length of 560 feet. We want to look at what happens to the bridge between winter and summer as it expands and contracts. So we need the coefficient of expansion for steel. That coefficient is 7.3 times 10 to the minus 6 inches per inch per degree Fahrenheit. That can be taken right off the internet from the Engineering Toolbox website. So, looking at the temperatures, if the bridge is 20 degrees during winter and then it warms up to 100 degrees in summer in the sun, we've got a difference in temperature of 80 degrees. So the strain that we get is equal to the coefficient of expansion times the change in temperature. So that gives us 7.3 times 10 to the minus 6 inches per inch per degree Fahrenheit times 80 degrees, or 584 times 10 to the minus 6 inches per inch. What that means for the bridge is that we get a total change in length of the strain times the original bridge length giving us a total change in length of 3.92 inches. Wow, that's a lot of movement.
That amount of movement would break the bridge apart if the supports tried to prevent it. The roller allows the contraction to naturally occur. This bridge in Vienna has a large roller to withstand heavy weights and large movement. Rollers are not always created by actually putting rollers into the structure. This bridge over U.S. Highway 151 has concrete girders that sit on rubber-like bearing pads instead of rollers. When the girders contract in length during winter, the pads deform, acting like rollers. A concrete slab bridge over the Mekong River has the slab sitting directly on the concrete abutment. We still think of this as a joint that can slip like a roller, but on the short span, contraction is small. Here a bridge has a roller joint between two pieces of the deck. The left segment sits on a shelf provided by the right segment. A bearing pad is inside the joint to allow the pieces to move apart during winter contraction. Roller joints that allow expansion and contraction aren't ideal in all situations. The Carquinez Strait bridges in California are so long that multiple contraction joints were needed. The two expansion joints shown in the diagram allow expansion in the summer and contraction in the winter to occur without pulling the bridge apart. These joints, however, actually separated the bridge into three parts, or three separate structures, shown shaded. The California DOT was concerned because during an earthquake, the three parts might vibrate differently, and they could slam together at the joints or maybe even pull apart. So they came back in and retrofitted the joints with special dampeners to prevent this. Many other bridges in California with roller supports failed when the motion became large and they fell off supports. When we are drawing sketches of structures, we will use a simple filled-in circle between plates to represent a roller joint or support. This roller can only transfer forces in one direction. Pin joints provide slightly more restraint compared to roller joints. A pin joint is like a hinge in a bicycle chain. The joint between links of the bike chain allows the pieces to rotate relative to one another but not pull apart. The Menai Strait Bridge actually uses the equivalent of a huge bicycle chain. What looks like cables are actually chains made up of 9 feet long links connected by pins. This is the Quebec Bridge over the St. Lawrence Seaway. If you look closely at the 2 top cords, you can see that they are made up of over a dozen steel plates or links like in a chain that are then pinned at the truss nodes. Here an assemblage for a pin joint where compression cords and diagonals all meet sits in the fabrication shop. The semicircular slots behind the men will hold the pin. This photo shows that same joint assembly on the bridge pier with the bottom truss cord and pins in place. A much smaller pin support is visible in this railroad truss over the River Lot in France. What is the advantage of pin joints? Well, the pin allows adjacent members to freely rotate so that no bending is applied by the joint. But the pin still holds the members together so there can't be any relative translation. Trusses use pin joints. The Navajo Bridge over the Colorado River was built by Kramer of Wisconsin in the 1990s. The pin joint at mid-span allows the 2 trusses built cantilevering out from the canyon on either side to be joined at mid-span without restraining relative rotation. Beams are often connected to columns with pin joints. In a steel I-beam, bending is resisted by stresses in the top and bottom flanges. If the beam flanges are not attached to a column, then no bending moment can be transferred. This is a pin joint. The webs are attached, restraining any relative vertical or horizontal movement, but rotation is not significantly restrained. Wood trusses are also usually built with pin joints. The small metal tooth plates used in the connections hold the pieces together. They restrain relative translation, but they are not stiff enough to restrain rotation. Actually, the bolted beam web and the truss plate do restrain rotation a bit. They provide what is called partial rigidity. Generally, in analysis, they are considered as pins. The symbol we will use to represent pin joints between members is a filled circle, or a circle on a triangle for a pin support. A third type of joint or support is a rigid one. A rigid joint restrains translation and rotation. The joined members are completely connected. A mock-up of a concrete beam-to-column joint shows the reinforcing used to transfer tension. The tension along with compression in the concrete allows bending to be transferred through the joint. These joints were used in a concrete building moment resisting frame. A concrete beam to column detail shows how bending forces are transferred through the joint, providing restraint of rotation. This is a joint between a precast concrete beam and a column. Joints like this were used to build a concrete skyscraper in San Francisco. Bolted joints between steel members can also create rigid joints. By bolting both the web to prevent translation and the flanges to prevent rotation, a rigid connection is obtained. Of course, welding can be used with steel. Here the web was first bolted to prevent translation, while the beam was held by the crane. Later, the flanges were welded to prevent rotation. When the lower beam in this San Francisco building is loaded, it bends and deflects. It tries to also bend the columns through the rigid joint. The columns, however, do not want to bend and actually reduce the deflection of the beam. So one of the advantages of using rigid joints is that deflections or deformations in the structure are reduced. Here we are looking at a rigid support. Steel piles are driven 80 feet deep into the soil. Then precast concrete bridge abutments are dropped over the piles. The piles slide into holes in the abutment, and the holes are filled with concrete. The abutment is then considered fixed to the ground. In our structural analysis, when we draw members with continuous lines at joints, no circles, we will take it as rigid. For supports, a member buried into crosshatching, like the pile buried in soil, will be considered as rigid, with no translation or rotation possible.
The reason we've paid so much attention to joints and supports is because it is essential that as engineers we communicate in a specific manner when describing structures. We've seen that there are real differences in the restraints and forces provided by the three different joint types. The roller joint restrains movement in one direction. Pins restrain translation in two directions. Rigid joints and supports restrain all translations and rotations.